Today we're going to look at limits of functions from tables or graphs. Suppose we're given y equals f of x, where f of x is defined to be 1 minus radical x over 1 minus x. And we want to calculate this limit. One of the things we could do is certainly draw a picture of this function. So let's try to see if we can draw a picture of this function. This is a function. This is going to be defined in the first quadrant. All of your radicand values. The domain of x is going to consist of all real numbers greater than or equal to 0 except for x equals 1. Notice if we plug in a 1 in the denominator of this fraction will become 0, and we would end up with 0 in the denominator, and that is undefined. And that's not any good. So, as we're drawing pictures of this, we want to be cognizant that we are in basically the positive x values, including 0. 0 is an absolute lowest bound, but we have to exclude the point x is equal to 1. And we can make a table of values. We can look at x versus f of x for specific tables of values. Now, when you're making tables of values, one of the things that you might want to try to do is use a calculator, either a scientific calculator or you can certainly do it by hand. But if we use a scientific calculator, in fact I'm using a TI-84 Plus, and we use these x values. We have 0, we have 0.1, we have 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. 1 we know we have a problem at, so it's undefined at 1, but we can certainly look at 1.1 or 1.2, values to the right of 1. So as we're calculating this idea using this notion of limits, these values, as I converge in on 1 from the left side, these are coming in from the left-handed side. And these values are coming in, into the limit from the right hand. These are right hand side limits. So let's plug in some of these values. At x is equal to 0, my functional value is 1. Then my values are approximately 0.76, 0.7, 0.65, 0.61, 0.58. You could do this on your own and see if you can replicate these same values. Of course I'm rounding off a little bit, so our numbers may be a little bit different. 0.56, 0.54, 0.53, 0.51, 0.48. Remember, x is equal to 1, this function is not defined. At 1.2, we're back to 0.47, 0.46. So let's stop here. And if we had to guess what the output would be when the input were 1, you might say somewhere in between 0.51 and 0.48. So you might guess, for example, 0.50. Now, if we draw a picture of the function, this guess, which is a numerical calculation of a limit, So you can see when someone says to calculate a limit of a function from a table of values, it's a lot of work. And there's some guessing involved, but you're making educated guessing. Now if you graph the function, at x equals 0 we have a y-intercept of 1, and your function appears to be decreasing. Certainly at x equals 1 we're going to have to put an open circle because our function is not defined at that point, but then it continues to decrease. So graphically it would seem as though this y value, which is a little bit off scale, but if you did it with a graphing calculator, you would see that the y value that this corresponds to is about 0.5 also. So it would be probably better to move the point up a little bit, but I'll leave it like that. So you can see that this would be a graphical computation. Now, we have a little bit of room to solve this analytically or symbolically. So let's see if we can do that here. If I'm looking at the limit as x approaches 1 of 1 minus the square root of x over 1 minus x, that would be equal to the limit as x approaches 1 of 1 minus radical x. Now this denominator is the difference of two squares. It's 1 minus the square root of x times 1 plus the square root of x. So what you can accomplish here is, we in mathematics say we have a singularity at x equals 1, meaning it's not defined at x equals 1. You can essentially remove the singularity by factoring the denominator as the difference of two conjugates, but you're factoring it over the set of irrationals. Normal factoring is done over the set of reals. Consequently, this limit is equal, or the set of rationals rather. Consequently, this limit is equal to the limit as x approaches 1 of 1 over 1 plus the square root of x, which as x approaches 1, this converges in on 1, and consequently the limit converges in on 2. So we were correct, whether it was with our guess or our graphical interpretation, and our guess was a numerical guess. We are calculating the limit numerically, which is an educated guess, or graphically, or analytically. In all cases, the limit turned out to be a half.